distance away.
But,
Careful.
oh. She'll remember the review session. Okay. Let me do maybe one or two more things, and then I'll ask you if you just guys want to call it a day or not. But I obviously I hadn't done everything. I knew I would never would have a chance to. Do you guys want to see practice with that reduction algorithm? I'm talking about for the chromatic polynomial. Let me just show you what I'm talking about. You guys know what I'm talking about? Okay, so this is problem number 20. This is actually the last one on the handout. I create this family of graphs called W sub n, which is the wheel graph. And what it is you have basically a vertex in the center, and then you have n. You have a wheel going around it. And the spokes go out from the center. So this is the graph, and there are n vertices around the outside, and then there's one more vertex in the middle. So the size of the vertex set is n plus 1. So for any n, you can draw that. Okay, so let me ask you just, I guess I've got 4 parts here, but most of them are quick. So my question is, for which values of n, part A, for which n is W sub n bipartite? Oh, by the way, I guess as a minimum, n should be at least 3. I can't really make a wheel if I only have 2 vertices around the outside of it. So it has to have at least 3 spokes. So for which values of n would this graph be a bipartite graph? Yeah. It's never bipartite. Was that everybody thought it was a trick question? Okay, basically, all right, you put this one color, right? You put your square around that. So then everything connected to that has to be a circle. Well, that means every other vertex has to be a circle. Well, that doesn't work, right? You have cycles of length 3 everywhere in this graph. So I don't care what n is, it's never bipartite. Okay, so that's good. That's easy. All right, here's part B. For which n is there a closed Eulerian trail? Why?
On the outside vertices have degree.
Tons of vertices of odd degree, right? So never. This is an exciting problem. Okay. Part C. For which n is there...
None.
That's a great guess. Well, you know what I'm going to come to next. Hamilton cycle. For which n is there a Hamilton cycle? Is all of them?
Yeah, just go all the way around, and then go in, and then back to 1.
So you start at, okay, so Davey says all. See, these are pretty easy. Basically, you just go 1 to 2 to 3, all the way up until you get to the second to last vertex, right? Which is n minus 1. Oh, I want to go all the way to n. Okay, good. I want to go all the way to n, and then go into the center, and then from the center, go back to 1, right? Alright, so this is a little, so we're specifically going to work with, we're going to specifically work with this graph here. 4 vertices around the outside and 1 vertex in the center. That's my W4 graph. So what I'm talking about here, this is the chromatic polynomial. Okay? So, you know, obviously whatever color, so the question is how many ways are there to color these vertices using K colors. Whatever color you choose to put on the center vertex, obviously you could start there if you wanted, there's K choices. The remaining vertices will never be able to use that color again. So you could say, well, there's then K minus 1 choices here, right? And then there'd be K minus 2 choices here. I mean, after all, here's a little cycle, right? And then this vertex, or well, we've only got 2 left. This vertex here has to be different from both of these two. So you can say, well, there's K minus 2 choices there. The problem is now, when you get to the lower right corner, since these opposite corners were not connected to begin with, they may or may not be the same color. And so that then affects how many choices you have here. So you either have to backtrack now and do cases, and you, instead of putting a K minus 2 here, you have to say, well, you know, case 1, you know, same color as that vertex, or case 2, different, and then you would then have to add those up, and that would actually be okay. You could work it that way, but there's a foolproof approach that doesn't involve all this careful analysis, which is to just use the reduction process. Okay, so do you guys remember how to do that? Should we practice it? You better practice it. Okay, so basically what you do is you create two other graphs. Sorry, I want to do this yet. Sorry. Let's start with W4. You create 2 graphs where you select 2 vertices that are adjacent to each other. So which 2 vertices do you want me to use here that are adjacent? It actually doesn't matter. The top 2? Okay, so X and Y like that. And what you do is you create 2 graphs. One of the graphs, you just remove that edge, but everything else is the same. So you're just going to remove that top edge. Okay, in the notes we called this G1. And then in the second graph, what you do is you merge those 2 points together. So you bring X and Y together. When you merge X and Y together, notice you also merge these those two edges. So you're going to get, so I have the triangle on the bottom, but now X and Y are going to come together. This is going to be XY like this, and it's going to be connected like that to the outside. Okay, and that's what we call G2. Make sense? That graph is actually what? It's what?
It's the equivalent of the 3.
Oh, it's a wheel 3? It is wheel 3, but it's also something else. It's K4. It's a complete graph on 4 vertices. And the benefit of knowing that it's K4 is that we already know the chromatic polynomial of Kn. The chromatic polynomial of Kn is literally just a falling factorial. So you just get however many vertices there are. In this case, 4 vertices, so you just start making choices on those vertices. So this would be your chromatic polynomial for G2. So I actually don't need to continue the reduction process for this graph because I already know what it's going to be. Now this one, maybe we don't know what this is yet. So we actually would then need to continue the process. So I have to choose 2 more adjacent vertices and play this game again. Does anybody have a suggestion for which 2 vertices you want to use in the graph G1? Doesn't matter. Great, bottom two. Thank goodness Davey's here, we make it out. If we get out on time tonight, it's thanks to Davey. Okay. Okay, good, so we're going to redraw these four vertices. We have the center, and we have everything coming out from the center, but we don't have the bottom edge. Okay, and then we have to merge the, so I'm going to get still this part, but then something like that, I think. When I merge X and Y together, whoops, no, I've also got to have this segment, like that. Okay? I think that's right now. Is that all right? So now this one I actually think we've done before. We can just analyze this one. We can keep doing the reduction if we want, but what I want you guys to be familiar with is that you don't have to reduce it all the way down. You can reduce these all the way down to null graphs if you want, but if you come across a graph that you say, hey, that's simple enough, I can now just analyze it, don't keep reducing it. You'll spend forever on the problem when you really weren't intended to. So with this bow tie, you can just say, oh, I have, a cycle of 3 over here. So, k minus 1, and k minus 2 on the left side. And then whatever color this vertex is, I just have to avoid it over here. So I have k minus 1 choices here, and k minus 2 choices here. You don't have to do any cases with that. I think we saw this one come up in the group work, and unfortunately in my solutions I decided to keep reducing it. You don't need to. You can literally just do that. Okay? Clear enough? And then on the other hand, well, over here this should be pretty doable as well. So you've got a cycle of 3, k minus 1, and k minus 2, and then this vertex, well, I just have to avoid these two colors. So that's just k minus 2. Right? So my final answer, I'm ready to go to a final answer now. It's just going to be the chromatic polynomial of G1, which comes from taking this one minus this one. So I'm going to have k times k minus 1 squared times k minus 2 squared minus k times k minus 1 times k minus 2 squared, and then minus this part, so that's minus k times k minus 1 times k minus 2 times k minus 3. So this would be the answer unsimplified, but it would work. Okay? And you'd be done. It could obviously be simplified somewhat. But I think I have a simplified answer in the solutions, so you guys can. You can check. So this is k times k minus 1 times k minus 2. You can factor that out. And it leaves you with k minus 1 times k minus 2. I just want to do this to make sure I did it right. Minus k minus 2 minus k minus 3. All right, so this is k times k minus 1 times k minus 2. And then on this one, it's going to be k squared minus 5k plus 7. That's what I got. It's over. That's the chromatic polynomial. Pretty nice. You guys, let me just talk through a couple of others. So I'm happy to call it a day. Let me just talk through a few of the problems I didn't go over and ask you if you'd like me to go over any of these. Showing that graphs are isomorphic or not isomorphic. I didn't practice that tonight, but do you guys know how to do it? Okay. You either look for a structural difference between the two graphs, or you give me the theta, which is the function that tells me how to associate the vertices of those graphs. Okay, so there's an example with a couple of examples. It's number 17. Isomorphic graphs have the same structural properties. So the one that's on here is that they have the same chromatic polynomial. So I think you did one in the homework where you proved that they have the same chromatic number. but proving that two isomorphic graphs have the same chromatic polynomial. That's kind of a nice example. It's not that difficult to prove it, and I've got the solutions, but I'm happy to go over any of these. I have a problem about just solving a recurrence relation, which is, we kind of went over that before, it's pretty easy. I've got the one with the arm wrestler, who's a champion for 75 hours, and he does at least one match every hour, no more than 125 matches. Sound familiar? Prove that there's a period of consecutive hours during which the arm wrestler had 24 matches. Way back at the beginning, right? I think there was one on the first exam that had to do with the guy catching fish. Just like that. Okay, so you guys can kind of look at that. And then there's a, well, that's just inclusion and exclusion. There's a couple with the, we didn't really do the Burnside theorem today. I'd be happy to go over one of those. I have a video that kind of addresses the, let me ask you this, okay, I think I will do one more problem. May I? Okay. Yeah. One more example, and this is, I'm just going to do part of one more problem. So I'm going to do problem 3B. Here's what it says. You have 8 colors. And you want to paint the 6 faces of a cube. Right? How many non-equivalent cubes are there? Now, if I stop right there and I just ask that question, you can just watch my video, and I do it for P colors, and you just plug in P equals 8. Basically, the symmetries of this cube, there are 24 of them. And I think I actually kind of went through them at the end of class on Wednesday. You can spin this thing like this, or like this, or like this, right? 3 different sort of directions used to spin it. Or you can spin it across 2 opposite corners, right? Like that. Or you can come across this edge in the front and just literally flip it over. And if you just consider all the ways of choosing edges to flip across or choosing opposite corners, you're going to get 24 different symmetries. And you can come up with a very nice formula. Okay. And so you would just, so you just watch my video, and hopefully it makes sense and it explains it. If it doesn't, it's a 15-minute video. You just, while you're relaxing at home, all your friends are watching TV, and you look like you're doing that too, but you're really watching my video. Somebody's got to be the nerd in the group, right? Anyway, but I'm going to give you one little twist here. How many non-equivalent cubes can you paint if each face must be a different color? So you can't just say, oh, I'm going to take the faces and paint them all red. You actually have to use a different color on each face. Okay. The question might be, well, how does that change the problem? The answer is it does not change it very much. So your answer for how you would solve that would be that you would still use the Burnside theorem. You would still divide by the whole group. You still have all of the same symmetries that you had before. That doesn't change. Okay. But for example, how many colorings of this cube are, okay, let me just draw a cube here. So originally, if you don't require the colors to be different, then you have, remember what you do in the numerator. You add up the number of colorings that are fixed by each symmetry one by one. And the first symmetry that we always look at, just to get us going, is just the do-nothing symmetry, the identity symmetry. So the identity symmetry will fix all colorings of this cube. Because if you take the cube and set it right back down the way it was, whatever the colors that you used on those faces is still the same. And so in that case, it would have been, you know, p to the 6th. P choices for each face. But I claim now, so in this case it would have been 8 to the 6th. 8 colors, right? For this first term. The first term in the numerator would be 8 to the 6th. I claim that that's not what it is now. What would the first term be now? Instead of 8 to the 6th, what would it need to be? Yeah, so well, just give it to me as a number, not the... Yeah! Wouldn't it just be that? 8 choices for which color you put on top. 7 choices for which color you put in front. 6 choices for which color you put on the right. 5 for the left, and so on and so forth, right? That would be it. Okay. Remember that when we're counting those colorings, we care about positions. So if I put red on this face and yellow on the top, that's different than putting yellow here and red here. That's different coloring. It might be equivalent, but it's a different coloring. Okay, so that would be, so we would want to count all of those. That would be your first term. Now, here comes the rest of the fun part of the question. We have 23 other symmetries, right? So, I have to ask how many colorings would be fixed by each of those other symmetries. So for example, if I painted the cube all red, if everything was red, then that would be a coloring that any symmetry would fix. Right? Doesn't matter what I do, it's going to still be all red and look the same when I set it back down. But if I have painted these 6 colors differently, and I rotate 90 degrees, is the coloring the same? I'm not saying is the coloring equivalent. I'm saying is it literally the same coloring? If I have taken the, I mean, actually I have 6 different colors up here. Okay? I don't know why I couldn't get some of them to be, they're all different, right? So if I have this coloring right like this, and I rotate it 90 degrees, is it still the same?
The colors are the same. They're in different
Is it the
positions.
same exact coloring of the cube? It's not.
It's not the same.
It's not the same. It's an equivalent. It's equivalent. Whatever I did here is equivalent to this. Equivalent colorings are where I can take one coloring, apply a symmetry to it, and get the other coloring. But they are not the same coloring, right? And that's because the colors have moved. If you do something to this cube other than leave it alone, you are moving faces around. And if you've moved faces around, if all the colors on the cube are different, then some of those colors have now moved, which means they weren't fixed by that symmetry. So when you start looking at that symmetry, or any of the 23 other symmetries, guess what? None of the colorings are fixed. You don't get anything else in the numerator. That's if the faces are different colors. Okay? In other words, if I have a vector of 6, okay. You remember the homework problems where you had like, you know, they had the vectors here, right, and you had to apply F or G. Oh, that reminds me, I have homework there. So get back to you. You know, remember we had like the blue, blue, you know, red, blue, blue, and then they gave you some permutation F, and you sort of applied it to it, and you looked at what happened here, right? My point is, what if these were 6 different colors? Blue, white, yellow, red, green, and turquoise. 6 different colors. Is there any F that you could apply to that that would leave it exactly the same that it is, other than the identity? The answer is no. So when you're doing your numerator, remember what is the numerator in this thing? The numerator is these guys, right? That's what's on top. So you're adding up all these terms, but what my claim is they're almost all 0. Because C of F is the set of colorings such that F star C equals C. Not equivalent to C, equals C. It has to be the same coloring again. Now, of course, if this coloring was blue, 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 well then sure, any of those other symmetries would fix that coloring if you're repeating blue. But if you have 6 different colors, must be a different color, every face is a different color, then none of those vectors, none of those colorings are going to be fixed by any non-trivial symmetry. Does this make sense? That's my point. I just thought I would show you that. So I didn't do that one on the video, but on the video I did the one where you are allowed to use the same colors again and again. Yes, Steve?
No, since we don't have the symmetry with the 24 be different than the symmetry.
So
will we still have the same symmetry?
we still have 24 symmetries. I can still do all 24 things here, right? I still have the same 24 symmetries. I still have 24 terms in the numerator. It's just that 23 of them are 0. It's because I don't have the same colorings actually. Remember, there's always two things that you're working with here. You're always working with a group of symmetries and the set of colorings. On this problem, when I say each face must be a different color, I'm changing what my set of colorings is. I'm saying the only colorings I'm allowed to have are colorings like this, where every single object being colored is different. So I'm shrinking C. My group G is still the same. Still have a 24 on the bottom. I still have 24 terms to add up in the numerator. But 23 of those symmetries do not fix any coloring that I'm trying to count. So in other words, do not fix the elements that are in my new set of things that I'm coloring. Yeah, Jeremy?
So G is not about the colors, but rather the orientation of the cube in this case?
Correct. The G has to do with what I'm doing to the cube. Rotating it, spinning it, flipping it over, right? All that, that's what the group G is, and that's not changing in this problem. The place where we saw the G change was in the group work when instead of a necklace, I gave you a merry-go-round. Okay? On that problem, on the merry-go-round problem, I said, well, you can still color, or you can make all the horses the same color. I didn't restrict you about coloring the horses. What I said, though, was it's a merry-go-round, which means you weren't allowed to flip it over anymore. Right? Does everybody remember that? The merry-go-round from the group work number 13, you only had 5 symmetries, not 10, because you couldn't do the flips. You have to flip the merry-go-round upside down. Okay, so in the group work, I had shown you that, yeah, you can change your group of symmetries. And this problem is just saying, well, you can also change your set of colorings. You can leave the group the same, but change the set of coloring. Are you guys okay with that? I can give you another one of those if you want. That didn't sound very enthusiastic. We can call it a day. I mean, it's here in the. Well, I'll just tell you what it was. I had another one where I said opposite faces are required to be the same color. Right. So if opposite faces have to be the same color, then for example, 90-degree rotation. Well, I have key choices here. Originally, I also had key choices here, but not if I'm saying opposite faces have to be the same color. If I'm saying opposite faces have to be the same color, I have key choices on this side, and then I don't have any more choices on this side, because it's got to be the same choice that I made here. And when I do my 90-degree rotation, well, whatever color is on top has to be the same as the color that's on the bottom. And I rotate it, so then this color also moves to the front and the back. So you're only going to have whatever color you pick right here on top is the same color that has to be on all the sides of this, all of the 4 moving sides of this cube. Right? So, I mean, it's kind of an intermediate problem. It's not so extreme as saying all the faces have to be different, but it's also not saying do whatever you want. It's saying opposite faces have to be the same color. So here's what I would recommend you do, because I do want to let you go. I would recommend you try that problem, which is problem 3C on the